Okay, hello everyone. So today I will run you through the new formulas on projectile at an angle. How did we derive them from both the kinematic equations and the trigonometric formulas? Now, so we can have a clear visualization of this, let me just draw a projectile launched at an angle like so. Okay, it has a parabolic trajectory, and we know that it is launched at a certain angle, and it has an initial velocity like so. Okay, so if we were to just get the velocity like this, and we were to get the angle that it's launched from the horizontal, we know that something like this has an x and y component. So if this is Vix, this would be Viy. Okay, so if you recall your vector components, how again do we get this Vix and this Viy? Well, let's start with Vix. So Vix, as you could see, this is the side adjacent to the angle. Okay, so if it's the adjacent side, then we can use the cosine in order to get it. So Vix is equal to Vi cosine of theta. Okay, now for Viy, this would be the side that is opposite to your angle, and therefore, in this case, we will now use the sine of theta. So that's Vi times the sine of theta. So this is how we get the x and y components of velocity in an angled projectile. And this is usually the first step because you have to separate x and y. You cannot mix them up together, and thus you have to compute first what is the x and the y component of the velocity. Now after you get the x and y component of velocity, if you recall our horizontal projectiles, the first step is usually to solve for the time, or how long it takes for your projectile to stay in the air. Okay, and in the horizontal projectile case, like so, we know that its bullet drop equals bullet fired. So in this case, we analyze that the time it takes to drop is equal to the time it takes to fly as a projectile, and thus we use the case of free fall of case 1, which is a dropped object. But in this case, it's no longer a dropped object because you launch it with an initial y velocity to the maximum height, and then it goes back down. This is actually parallel to hang time. And as such, if it's parallel to hang time, then we know that we have to account for the fact that it goes up and down. Okay? And we also know that the velocity at the top is equal to 0. So this is a case of free fall of upward motion. And in order to get the time, we can start with the kinematic equation. Vf is equal to Vi plus At, but I'll use Ay, okay? With Ay is equal to negative 9.8. Okay, so how do we then get this? Well, I think it's much easier to analyze this knowing the fact that Vf is equal to negative Vi. Okay, because the velocity at this point, the Vi, once it goes back down, it has the same velocity but in the negative direction. Okay, so Vf is equal to negative Vi. So we can simply rearrange this. So we can say that negative Vi is equal to Vi plus Ay. We know that this is going to be negative g, and it's going to be multiplied to the time of flight. Okay, let me label this Tf because it's time of flight. Now, we can rearrange this. We can move this to one side. We can get negative 2 Vi, and I think it's now important to specify that this is in the y direction, and there's a negative gt in the one side. We can move the g to one side and get negative 2 Viy over negative g is equal to the time of flight. Okay, there are two negative signs, so we can just simply erase this negative sign like so, and we're going to get 2 Viy over g is equal to time of flight. However, it does not end there because we know that this Viy can be substituted. Okay, this Viy can be substituted using this relationship, and thus the time of flight of an angled projectile would be equal to 2 times the Vi sine of theta all all over g, gravity. So this is the formula in order to get your time of flight. Take note, g in this case is positive 9.8 because we know that VIY, or the VI it was launched, is positive, and thus time of flight has to be positive. It cannot be negative. Time doesn't go backward, and thus time has to be positive. Okay? So now that we know our time of flight, we can now think, okay, how do we then get delta y? So this is time of flight. Let me just write this to be a bit more organized. This would be components of velocity. So now that we have the time of flight, we can then use this to get two more things, delta y and delta x. So let's start with delta y, or your maximum height. And in order to do this, we can then look at the case of free fall again. Let's go in the going up direction. We know that in this case of free fall, where one object goes to the top, we know that VI, y, is equal to something positive, but at the top, VFY is equal to 0. Okay? We know that this is affected only by gravity. Okay? Negative g, or that's your acceleration, and this is equal to negative 9.8 meter per second squared. And we also know that we're looking for delta y, which is the maximum height. So we're analyzing this like the case of free fall. Now, which equation has all of these put together? Well, we can then turn to the fourth kinematic equation, which is the combination or the dots equation, and that's equal to Vf squared, but I'll specify this to be in the y direction, is equal to Viy squared plus 2a in the y delta y. Okay, so that's the fourth kinematic equation. Now, let's make some cancellations. We know at the top, Vf is equal to 0, so this cancels out. Okay, so we can then also know that this Ay, let me use a different color, we know that this is equal to negative g. Okay, so if we rearrange this, we could get 0 is equal to Viy squared minus, because there's a negative sign, 2g delta y. Okay, so we can rearrange this, put everything to one side except delta y. We get negative Viy squared all over negative 2g. That's equal to delta y. Now we can then cancel out the negative signs, make them positive, and we can finally come up with the form Viy squared all over 2g. But we also know that this Viy can again be substituted for this Viy, Vi sine theta. So substituting, we can get that delta y is equal to Vi sine of theta, but squared all over 2 times gravity. So this then would be your formula in order to get the maximum height of your projectile at an angle. Okay? So we've solved for the components of velocity, we've solved for time, we've solved for maximum height. Now the last thing that we have to take a look at would be delta x, which is the range of your projectile. Now if you recall your horizontal projectiles, okay, your bullet travels a certain time, which you will solve, and you will simply multiply this to the velocity, and that will be your delta x. And in an angled projectile, it's actually no different. But this time we have to account for the fact that it's an x velocity. So we can use the kinematic equation. Delta x is equal to Vi xt plus 1/2 axt squared. However, we know that a of x is equal to 0. Okay? And why is that? Because we know that in projectile motion, you do not accelerate horizontally. You only accelerate vertically due to gravity, but not horizontally, because no other force acts on your projectile except gravity. So delta x is equal to vi xt. We can then substitute delta x to be delta x is equal to vi cosine theta times your time of flight. Okay, this seems to be simple enough, so I'll encircle this. However, if you actually know a bit of advanced trigonometry, we can simplify this further such that you can go directly to delta x without even computing for your time of flight. And how do you do that? Well, time of flight, we know, is equal to this. So if this is time of flight, we also know that that's equal to this formula over here. So we can substitute that to get delta x is equal to cosine of theta. Okay, and we can get this entire thing to vi sine of theta over g. Okay, now it seems like we're going nowhere, but there's actually a trigonometric identity that we can use. So I'll just put this in a different color, and you can probably get to this point when you get to the trigonometric portion in math, which is further down this term, or maybe in senior high school. But there's a trigonometric equation that goes to, is equal to cosine of theta sine of theta. Okay, so as you could see, this trigonometric identity can be used to substitute for this and this. Okay, so if we simplify this down further, we can get a form that goes, let me just rearrange it a bit. So that's delta x is equal to, we have the 2 on one side. We know that vi times vi is vi squared. And we have cosine theta times sine of theta. That simplifies to sine of 2 theta. That's a double angle over g. Okay, so in order to get the range of your projectile, all you have to do is get vi, get the angle, and you can plug it into this equation. Just have to multiply the angle by 2. Just have to multiply this angle by 2, and you can just simply get delta x. Okay, so these are your 4 equations for angled projectile. You can also solve this using kinematic equations, but this one would simplify your life because you're essentially using just vi alone. You don't need to do the step-by-step formula of getting the time of flight, then computing the delta y or the delta x. You can just go direct once you're given a vi, and once you're given an angle, you could then solve for these quantities. So anyway, thank you for watching. I hope this video was helpful, and I hope that this would simplify your calculations for angled projectiles. Take care.